Excellent. Okay, so I'll get ahead and start. Okay, so this is pretty much, thanks for coming today, everyone. I'm Donald Christie, and this is pretty much my presentation on forward stratigraphic modeling with ONLAP 2D for reservoir prediction in that area. So here's an introduction. On the right-hand side, we have the Gulf of Mexico, and in the south, we have the Sureste Basin. Now, this basin has a wonderfully complex geological history, which unfortunately I haven't got time to go into, but can provides us a fantastic opportunity to explore the use of forward stratigraphic modeling in the aid of exploration in deep water areas. And within this green box is our study area somewhere in there. And we have, see on the left-hand side here, and we have two cross sections as well as well A. Now our study area has 4 mini basins labeled here, and we have the most important structural highs labeled here, high 1 and high 2, and we have multiple salt diapirs. This is clearly a structurally complex deep water sedimentary system. Now within this study area, there is good quality seismic. It's not great, because it lacks the vertical resolution to image the detailed stratigraphic relationships. And while the overall tectonic history of the Sureste Basin is well defined, in our study area, this is not the case. So what I'm going to do today is hopefully illustrate how we've used ONLAP 2D to help do just that, which is to better understand the tectonostratigraphic evolution of this deep water system in the late Miocene, and hopefully improve the understanding of how sediment deposition and structural processes have evolved within the study area. So on the right hand side, next one here. So what is ONLAP 2D? Well, ONLAP 2D is a 2D based combined structural and stratigraphic forward modeling program. It simulates the tectonostratigraphic evolution and development of structurally controlled deep water mini basins. It's designed to be used in areas with imperfect subsurface data. So a quick refresher, geometric based models do not take into account the processes of deposition, unlike process-based stratigraphic forward models, and instead work by averaging deposition over a set period of time, taking into account only the essential behavior within a sedimentary system. ONLAP 2D uses simple rules to precisely match subsurface data from the real world and iterates towards a best fit solution through hundreds of simulations. So before we get into the deep dive of our model cross sections, I need to take a quick look at the basic inputs of our model, and we're going to start off with the boundary conditions, where we have the total simulation time for the simulation of 12.2 million years from the middle Miocene up to present day, which gives us time per time set of 50,000 years and a total number of time sets of 244. The total basin length for line 1, 8,550 meters, for line 2, 10,875 meters. And we have a horizontal resolution within our model of 25 meters. This essentially means as the horizontal distance that each cell within the model is representative. So what are our physical inputs? Well, we start off with our initial sea floor topography, which is simply the height in meters from the lowest point in the model. We then have a structural growth profile in rate, which is the amount of rise applied in millimeters per year to the basin structure through vertical shear converted to meters per time step. We then have background sedimentation rate, which is the amount of sediment deposited uniformly along the cross section through both pelagic and hemipelagic settling in millimeters per year. And finally, we have our clastic, a rate of rise of a clastic emitting surface. This is simply land that delineates above which no gravity flow deposits are preserved and below which, if there is accommodation, gravity flow deposits are preserved. The key points here are these key physical inputs are based on real structures observed from seismic and well data, and they're independent of each other. However, ONLAP combines them using simple rules to create realistic looking basin architectures, such as this, which is the tectonostratigraphic evolution of line 2. And here we have position of well A. So what we have here is a side-by-side comparison of the ONLAP 2D model and our geoseismic data. In yellow, we have gravity flow deposit packages. In light gray, our background sediment. And then darker gray, we have our basin structure. Now, as geologists, geoscientists, or scientists, we often associate the color yellow with sandy lithologies. However, in ONLAP, yellow does not necessarily represent a sandy lithology. It simply represents any sort of sediment that has been deposited through gravity flow. such as low density turbidite, debrite, all the way up to mass transport complex. It's up to the geologist with their own knowledge or regional data to make an interpretation. Now, we can compare our model that I put to line 2 of our geoseismic of line 2. We find that overall the model basin structure and thicknesses of the zones within an interval of interest, as well as the lateral extent of the gravity flow deposit packages within these zones, were a good fit to both our seismic and our well data. But one thing to notice is that above our section of interest, we have this wedging geometry. This is not as fine-tuned as our section of interest, however, can still provide important information. So what we're looking at here are the input parameters for line 2. On the top left, we have our structural growth profile with basin position on the y-axis, time on our x-axis, and then the rate of structural growth rise on the vertical axis. We then have a classic limiting surface, a rise with time on our x-axis, and then the amount of rise units per time step on our y-axis. And you can see it's very sporadic in terms of the amount of rise per time step and the length of that rise. We then finally have our background sedimentation rate. We have time on the x-axis, y is basin position, and the thickness of background sediment deposited is on the vertical axis. This one was uniform through time, uniform in space, but evolves through time. Now, if we cast our minds back to the last slide, I mentioned a wedging geometry seen above our section of interest. So to fit the stratigraphy above our section of interest, we required 2 different components to our structural growth rate profile with different growth histories. One profile incorporating compressional folding around high 1 and salt tectonics around high 2. It was this combination of complex multi-phase structural growth profile, a background sedimentation rate derived from multiple condensed sections within well A, and a variable rate of rise for classic limiting surface that varied both in the magnitude of rise per time step and the duration of each rise, provide us the closest fit to our seismic and well data of multiple model runs. So what we're looking at here is a 3D diagram of the structure as it goes through time. A bit complex, but I'll quickly run us through it. Hopefully we can understand it quicker. So what we're seeing here on the where was I? All right, so what we're seeing here is a 3D representation of the structural growth profile. We have time, so basin position on the y-axis, time on the x-axis, as well as a chronostratigraphic chart to translate time to time step easily, and then a vertical axis, which represents our rate in meters per time step that our structure grows. We also have the position of well A here. Hopefully you can see that. Now, phase 1 of compressional folding occurs between time step 0 to 65, with the maximum amount of flow growth occurring between time steps 50 to 59. Folding then dies down, and at this point, salt tectonics, which is continuous throughout history, becomes dominant. Phase 2 of our compressional folding begins at time step 80, with the maximum flow growth occurring at time step 88. And at this point in time, salt tectonics continues throughout time, and our full growth over high 1 begins to die down, which gives us this wonderful wedging structure that we saw in the past slides. So aiding in areas of imperfect subsurface data is what OnLabs 2D was designed to do. I'm going to be able to make predictive statements about the thickness, lateral extent of gravity flow deposit packages and their backgrounds and background sediments. And through integrating the model outputs with interpretations of subsurface data, from, for example, well data, we can make predictive statements about stratigraphy away from well control. So I'm going to look at some interpretations of, take some interpretations of data from well A provided to us and combine them with a final simulation for line 2 and make some predictions about stratigraphy in minibasin 4. So what we're looking at here is evolution of line 2 from time step 1 up to time step 45. This is zone 1 and zone 2, you can see on the right hand side here. And within zone 1, we see sedimentation occurs relatively infrequently over a long period of time, with only a small number of thick gravity flow deposit packages that do not overwhelm our structure. Now moving through the stratigraphy into zone 2, we see sedimentation becomes more active at this point in time. We have a high number of gravity flow deposit packages being modeled to be deposited. And these are simulated to progress the OnLab on 2 and crest over high 1, where thin sediment gravity flows are intersected by well A. Now, if we cast our mind back a few minutes ago, I said phase 1 of the compressional folding around high 1 is active throughout this period of time. The implication of this is that OnLabs 2D predicts that during this point in time within the late Miocene, from 12.2 to 10 million years ago, we have a strongly confined deep water system in a structurally active mini-basin that has become progressively unconfined through time as sediment flux overwhelms the growth of structural accommodation. So let's zoom into this red box and take a closer look. The sediment gravity flow deposit packages penetrated by well A from zone 2 were interpreted from the well data to represent distal low fringes. We can clearly see that the modeling predicts that these gravity flow packages thicken into mini basin 4. So if we combine this interpretation given to us, what we can deduce from the model is that there's the suggestion that zone 2 represents a lobe system that has become progressively unconfined with time as sediment input has outpaced the growth of structural accommodation.
You have 2 minutes.
Thank you. Now, looking at zone 1, sediment gravity flows are not penetrated by well A, therefore we cannot definitively state their lithology. What we can say is that these flow deposits modeled here are likely to be strongly confined deep water turbidites, potentially making them more sand prone. Now, if we focus on the position of stratal terminations within zone 1, we can see that OnLabs 2D predicts the positions of their pinch out, which is a crucial information if you're looking for example, stratigraphic traps. And the pinch outs of these gravity flow deposits move progressively away from the underlying structure itself, which is a region-wide correlatable mid-Miocene unconformity. Crucially, this means that OnLabs 2D predicts where your stratal terminations, your OnLab positions are, which you cannot see due to imperfect seismic data set. And it predicts thick, extensive background sediments above and below within this zone. So, in conclusion, what I've done today, hopefully, is talked about how OnLabs 2D has taken existing subsurface data, hopefully adds a little bit of scientific value and commercial value to it by combining it with forward modeling. It simulates the tectonostratigraphic evolution of real-world basins from imperfect subsurface data and can provide insight into the timing, magnitude, and geometry of controlling structural processes, as well as make predictions and statements on the distribution, thickness, and lateral extent of gravity flow deposit packages, as well as the background thickness away from direct well control. And that's my presentation. Thank you for listening.
Thank you very much, Donald, for this very interesting presentation. It's a kind of modeling I haven't seen before myself. So it's great. I don't see any questions. Joris, do you have a question?
Sorry, can you say that again? Oh, sorry.
Yeah, Joris is on. Joris, do you have a question?
Well, you mentioned that we shouldn't necessarily equate the yellow color to sandy deposits. But could you comment perhaps a little bit on the lithology information that well A gives you about these sections that you just described?
Sure, I can go a little bit. I'm not allowed to say too much about exactly what's in the well because they're it's not being released. It's not public data. I am kind of confined in that sense, but I can tell you there was a decent amount of information. There was the usual well log suite you get in there. And I think there was cuttings, sidewall cutting. I'm not entirely 100% sure. I can't really comment on that. But we basically use that information to really kind of define, and what the most crucial part was the condensed sections, which allowed us to calculate a background sedimentation rate, as well as the kinds of lithologies you get in there. We do know from the well data provided us from well A the types of turbidites and turbidite currents that were found in that. So from there, we've made our inference of what we may be seeing in mini basin 4. Does that answer your question?
Yeah, I don't want to get you into trouble.
Yeah, I mean, yeah, I would honestly speak about it more openly if I was allowed to.
Sure, sure.
But I don't want to get too much trouble.
Okay, thank you, Roger, very much.